Welcome back, everyone. Ready for another deep dive?
Always ready to explore.
Awesome. Today, we're looking at something that might seem basic at first. Earth's movement through space.
Smells familiar.
But trust me, this is going to be way more than just that simple orbit around the sun we all learned about. We're diving into some seriously cool insights from this YouTube video called The Real Movement of Earth Through the Galaxy. It's from the channel Space Matters.
YouTube, huh?
Yeah, I know what you're thinking, but this video's got some seriously good stuff in it.
Okay, you've got my attention.
So, to kick things off, let's start with that orbit around the sun, right? We all know it's not a perfect circle.
Right, it's an ellipse, like a slightly squashed circle.
Exactly, an ellipse. So, what does that actually mean for us here on Earth?
Well, it means our distance from the sun actually changes throughout the year.
So, we're not always the same distance away.
Nope. There's a point where we're closest, called perihelion, and a point where we're farthest away, aphelion.
Perihelion and aphelion. Gotta love those astronomy terms.
And get this, those points actually line up with some pretty familiar dates, January 3rd and July 4th.
Hold on, so we're closest to the sun in January, in the middle of winter.
Yep, that's right. Seems counterintuitive, right?
Totally. You'd think we'd be closest during the summer when it's hot.
You would. But the seasons are actually caused by the tilt of the Earth's axis, not by our distance from the sun.
Right, the tilt, of course.
But those changes in our orbit, even though they're subtle, and the changes in Earth's tilt and wobble over time, they can really impact our climate over, well, tens of thousands of years.
Tens of thousands of years.
Yeah, we're talking long-term changes here.
Okay, now I'm really intrigued. What kind of long-term changes are we talking about?
Well, scientists call them Milankovitch cycles.
Milankovitch cycle.
Yeah, and they're pretty fascinating. Imagine, like, the Earth's tilt slowly shifting over, millennia, kind of like a spinning top starting to wobble.
I can picture that.
And that change in tilt, along with the slight shifts in our elliptical orbit, well, they can affect how much sunlight different parts of Earth get. And that leads to those long-term climate patterns. Even things like ice ages.
Wow, so those ice ages, they weren't just random.
Not random at all. They're actually influenced by these subtle changes in Earth's movement. Crazy, right?
Absolutely mind-blowing. But hold on, our solar system isn't just sitting still in space, is it?
You're catching on. There's a lot more to this movement story.
Yep. I had a feeling. Okay, lay it on me. What else is going on?
Well, for starters, we're actually zooming around the center of the Milky Way galaxy.
Okay.
At an incredible speed, I might add, 143 miles per second.
Wait, 143 miles per second? That's like going from New York to Philadelphia in the blink of an eye.
It is incredibly fast.
So we're on a galactic roller coaster.
You could say that. But of course, it takes a long, long time for us to complete one full orbit around the galactic center. About 230 million years.
230 million years. Wow. Okay, my brain's trying to process that number. But hold on. I thought things farther out in a spinning system moved slower, right? Like the outer planets in our solar system. Doesn't that apply to galaxies too?
Absolutely.
Yeah.
Just like in our solar system, stars closer to the center of the Milky Way, they move faster than those farther out. Gravity is the key player here.
Right. The closer you are to that supermassive black hole at the center.
Exactly. The stronger the pull.
Yeah.
So you have to move faster to stay in orbit. Makes sense, right?
Yeah, totally. So we're whizzing around the galaxy, but there's more to it, isn't there? The video mentioned something about the sun doing a cosmic dolphin impression.
Ah, yes. The sun's motion isn't just a simple flat orbit. As it travels, it also bobs up and down through the plane of the Milky Way.
So up and down like a dolphin.
Exactly. Like a dolphin leaping in and out of the water. Pretty cool, huh?
Okay, that visual is amazing.
Mhm.
So we're spinning around the sun, which is whipping around the galaxy, A and D, doing this cosmic dolphin dance. This is getting pretty complex.
Oh, we're just getting started. And this next part is where things get really mind-bending. Because you see, the Milky Way itself is moving too. Yeah, it's true. It might feel like we're standing still here on Earth, but our whole galaxy is drifting through space.
Yeah.
Like a ship on a vast cosmic ocean,
Well, okay, so if everything's moving, how do we even know the Milky Way's in motion? Like, what's our reference point?
Ah, that's a great question. It all comes down to perspective. Imagine you're walking down the aisle of a train, and the train's moving at a steady speed.
Okay, I can picture that.
So from your perspective, it feels like you're just walking normally, right?
Yeah, yeah.
But to someone standing outside watching the train go by, you're clearly moving pretty fast.
Ah, so it all depends on your point of view, your frame of reference.
Exactly. It's like a fundamental concept in physics. And just like with that train example, when we talk about the Milky Way's movement,
Hmm.
we need a reference point to really understand it.
So what reference point do we use for the Milky Way?
Well, one way is to look at other galaxies, you know, see how they're moving relative to each other.
It's all about those relationships.
Yeah, it's all connected. Astronomers can kind of piece together the overall motion of our galaxy by studying how these other galaxies are moving.
So by observing these galactic dances, we can see that the Milky Way isn't just sitting still.
Exactly. It's moving along with all the others.
Hey.
And remember that dolphin motion we talked about? How the sun bobs up and down?
Oh yeah, like it's on a cosmic trampoline.
Right. Well, when you combine that bobbing with the Milky Way's overall movement through space, it creates a path that's not a straight line.
Ooh. What is it then?
More like a spiral.
A spiral. So our galaxy is like doing a giant corkscrew through space.
You got it. It's not just moving forward, it's rotating too.
Yeah.
And that combo,
Oh.
it creates this like three-dimensional spiral path. Pretty wild.
Okay, that's seriously complex. But I'm loving it. So we've got Earth spinning around the sun doing its dolphin dance around the galactic center, and now the whole Milky Way is spiraling through space. But hold on. We were talking about that great attractor earlier. Where does that fit in?
Right. That's the next layer of this cosmic onion. Remember, our Milky Way is just one member of a larger group of galaxies, right? Called the local group.
Yeah, the local group.
Well, it turns out our whole local group is being pulled toward this mysterious region, the Great Attractor.
So it's not just our galaxy, it's a whole bunch of them being tugged in the same direction.
That's right.
What eye is this great attractor, and why is it so powerful?
Well, that's the big mystery. We know it's somewhere around 150 million light years away,
Yeah.
and we can see its gravitational influence on galaxies, within hundreds of millions of light years.
Yeah.
But its exact nature, it's still a puzzle.
So we're talking about something that can pull on entire galaxies across these vast distances, and we don't even know what it is.
Pretty much.
That's kind of sad.
It definitely sparks the imagination. Of course, astronomers have some theories. Could be a massive supercluster of galaxies, like much larger and denser than anything we've ever seen. That kind of concentration of mass would have a serious gravitational pull.
So like a cosmic metropolis.
Yeah.
A giant cluster of galaxies all huddled together.
Yeah, you could think of it that way. Another theory is that it could be a region dominated by dark matter.
Dark matter. Oh, now we're getting into some serious mystery territory. Remind me, what exactly is dark matter?
So it's this type of matter that doesn't interact with light, so we can't see it directly. But we know it's out there because we can see its effects. It's gravity pulling on visible matter.
So it's like this invisible scaffolding holding the universe together.
That's a great analogy. And some scientists think that the Great Attractor could be a region where this dark matter is super concentrated, like a gravitational well pulling in all the surrounding galaxies.
So we've got these two main theories then. A supercluster of galaxies or a super dense region of dark matter. Any other contenders out there?
Well, some scientists have proposed some more exotic possibilities. Some think it could be a supermassive black hole, like millions, maybe even billions of times bigger than the one at the center of our own galaxy.
Wow.
Others think it might be a region where the fabric of space-time itself is warped in ways we don't understand yet.
Okay, now those theories are venturing into science fiction territory, but that's what makes this so fascinating, right? We're talking about this fundamental force that's shaping the movement of galaxies, and we're still trying to figure out what it is.
Totally. It really shows you how much we still have to learn about the universe.
But wait, there was one more layer to this whole cosmic onion, wasn't there? Something about the universe itself expanding.
You have a good memory. And yeah, this might be the most mind-boggling part of all.
All right, hit me with it. I'm ready.
All right, so imagine a loaf of raisin bread dough rising in the oven.
Raisin bread. Okay, I'm intrigued.
So as the dough expands, the raisins, which let's say they represent galaxies and move farther apart, right?
Okay, I'm following.
Well, that's basically what's happening with the universe. The space between galaxies is stretching, causing them to move away from each other.
So it's not just that galaxies are moving through space, it's that space itself is expanding, like everywhere.
Exactly. It's like the entire universe is a giant balloon that's constantly being inflated.
Wow.
And here's the kicker. It's not just expanding, it's expanding at an accelerating rate.
Hold on. You're telling me that on top of all of this other movement, everything's getting farther apart at an ever-increasing speed. This is next level stuff.
It is pretty wild. But even with all this cosmic chaos, there's something that can act as a kind of anchor for us.
An anchor? I could definitely use one right about now. My head is spinning.
It's called the cosmic microwave background radiation, or CMB for short.
CMB, what is that exactly?
Think of it like the faint afterglow of the Big Bang. That event that created the universe, this radiation, the CMB, it's everywhere throughout the entire universe, and it's incredibly uniform, no matter which direction you look.
So it's like a cosmic echo of the Big Bang. But how does that help us understand movement?
Well, by measuring tiny variations in the CMB, scientists have figured out that Earth and our whole solar system, we're moving through the universe at about 370 miles per second relative to this background radiation.
So even though everything's moving, we can use the CMB as a reference point to understand our own motion.
You got it. It's like our cosmic speedometer. Helps us make sense of where we are in this vast and ever-expanding universe.
Okay. I think I need a minute to process all this. We started with Earth's orbit, zoomed out to the Milky Way, spiraling through space, and now we're talking about the expansion of the universe and cosmic speedometers.
It's a lot to take in, that's for sure. But pretty awe-inspiring, don't you think?
It really is. It makes you realize how much we still don't know about the universe and our place in it.
Absolutely. We're just scratching the surface of all these cosmic mysteries.
I know. It's crazy to think about all this movement happening like all the time. We're spinning, orbiting, spiraling, expanding. It's kind of hard to wrap your head around it all.
It really is mind-boggling. You know, for a long time, people thought Earth was the center of everything. Like it was all just revolving around us.
Oh, yeah, the geocentric model. We've come a long way since then, huh?
For sure. It just shows how much our understanding of the universe has evolved, you know? The more we learn, the more we realize how much we don't know.
Speaking of things we don't know, that great attractor is still a big old mystery, right? What are some of the leading theories about what it could be?
Well, one of the main ways is that it's just this massive concentration of galaxies, like a supercluster, but way bigger and denser than anything we've ever observed. That much mass would definitely have a powerful gravitational pull.
So like a cosmic metropolis, a giant cluster of galaxies all hanging out together.
Exactly. Another theory is that it could be a region dominated by, you guessed it, dark matter.
More dark matter. Okay, we're back in the mystery zone.
Right. It's this invisible stuff, basically. Doesn't interact with light, so we can't see it directly.
But we know it's there.
Yep, we can see its effects. Its gravity tugs on the stuff we can see.
So like an invisible scaffolding holding everything together.
Perfect analogy. And some scientists think the great attractor might be a place where this dark matter is super concentrated, creating this like gravitational well that pulls in all the surrounding galaxies.
So we've got the supercluster theory, the dark matter theory. Are there any other ideas floating around out there?
Oh, some scientists have come up with some pretty out there ideas. Some think it could be a supermassive black hole, like millions, maybe even billions of times bigger than the one at the center of our galaxy.
Whoa, okay. That's a big black hole.
Others think it might be a region where space-time itself is warped, like in ways we don't fully understand.
Okay, now that is definitely getting into science fiction territory.
Right. But that's what I love about this stuff. It's like we're talking about this fundamental force that's shaping the movement of galaxies. And we're still trying to figure out what it asks.
Exactly.
Yeah.
It really shows you how much we still have to learn about the universe and our place in it.
Couldn't have said it better myself. We've covered a lot of ground today, haven't we? Started with Earth's orbit, zoomed out to the Milky Way spiraling through space, explored the mystery of the great attractor, all while the universe keeps expanding around us. It really makes you think, huh?
It really does. It's amazing to think we're all part of this incredible cosmic dance. And there's still so much out there to discover. So to everyone listening, keep looking up, keep asking questions, and never stop exploring the wonders of the universe. Until next time.